So welcome to Math 150, Multivariable Calculus, Section 2, Lecture 3. What we're going to do today is we're going to talk a lot about dot products, cross products, stuff like this. As long and as technical as these discussions are going to be, as boring as they may be in some places, remember, I have to do this twice. Okay, so it could be worse. You could be up on this side of the blackboard. What I want to do is I want to try to highlight the bigger picture of why these things are true. And I want to really emphasize doing special cases and building intuition from special cases and going from there to the general case. I'm going to use a lot of linear algebra. Is there anybody here who has not seen 2x2 matrices and matrix multiplication? Okay, so I'm not expecting you to be masters at this. A lot of this is to just prepare you so that if you go on to linear algebra, it's also to see the right way of doing things, that if you look at things the right way, the algebra becomes a lot better. And so I'm not going to give full proofs. I'm going to prove good special cases and talk to you again about building intuition. This is similar to what we did last time when we looked at the formula for the derivative of a product. I didn't prove it, but I justified it in several cases. So we have the dot product. We have V dot W is V1 W1 plus Vn Wn. And we can write this with summation notation to sum k goes from 1 to n of Vk Wk. We can define anything we want in mathematics. Most definitions are worthless. This turns out to be a good definition. Now, the big theorem we have is that V dot W is the length of V, the length of W, times the cosine of theta. And here's V, here's W, here's the angle between them. If I wanted to truly cover the blackboard in chalk, I could call this theta sub VW to highlight that this angle depends on V and W. Right now, this is the start of the class. The board is pretty clean. There's only two vectors, V and W. There's only one angle, the angle between them. So there's really no need right now to put on too much notation. Later, if we have 6 different vectors and 3 different angles, which angle am I talking about? Which one is that? Then it's better to put that down so I can quickly look. This is a wonderful result. V dot W is very easy to compute. I just take the pairwise products and add. I can multiply, I can add, not a big deal. And it says that it's related to the angle between them. Now you always want to be careful, what is a definition and what is a theorem? So we do not know that many fundamental theorems at this point in our careers. You have seen possibly 2 fundamental theorems before the fundamental theorem of calculus, which should be the 3rd fundamental theorem you've seen. Does anybody recall any fundamental theorems? No. It's a wonderful theorem, and we will mention the intermediate value theorem later today, but it is not a fundamental theorem. Except for probability, the fundamental theorems have fundamental as part of the name. The fundamental theorem of, so there's the fundamental theorem of algebra. A polynomial with complex coefficients of degree n has exactly n roots with multiplicity. There's the fundamental theorem of arithmetic. A number can be written uniquely as a product of primes of increasing order. And this is why 1 is not considered a prime. Because if 1 were a prime, we would lose unique decomposition. There is the fundamental theorem of calculus. And if I give you some function f of x, and here's a, here's b, and assume big F has little f as its derivative, then the area under y equals f of x from a to b is big F of b minus big F of a, and we write this as the integral from a to b of f of x dx. If you drop the word area, I think I'd have to say that's worse than rooting for the New York Knicks in terms of making me mad. Cultural extra credit, which superhero has the catchphrase, "You wouldn't like me when I'm angry"? Hulk. You will get me extremely upset if you drop the word if. And if you say that the integral of a to b of f of x dx is big F of b minus big F of a, who cares? At that point, it's a definition. The content is that this is the area under the curve. That's why this is so important, is we can now calculate areas by using antiderivatives. So the word area is absolutely essential here. We have many different things we can define. The dot product is one. If I give you two vectors, what kind of quantity is the dot product? Scalar, it's a number, excellent. If I take two vectors and I take the cross product, what kind of quantity is it? It's a vector. And so the cross product does not exist in every dimension. It exists in 3 dimensions, and we will use it extensively. This is a definition. This is the theorem. This is the content. So whenever you see a theorem, you always want to try to get a sense of what is it saying? Is it reasonable? What if I were to double the length of v? What would happen to the right-hand side if I double the length of v?
The right-hand side?
Yeah, to this side. What happens if I double the length of v? It doubles. And what about v dot w? If I double v, what happens to that sum? Double, because I replace every v with twice its value. If I triple v, I triple this side, and I would triple each term here. That's reasonable. It makes sense that I should have a length of v on the right-hand side, because if I'm doubling v or tripling v, that's how it's going to come. So without loss of generality, we'll see later that I might want to just consider the special case when v and w have length 1. I can always adjust things to have length 1, except for one quantity. There's one number that I can't rescale to 1. What is that one number? 0. No matter what I multiply 0 by, it's still 0. But if I'm looking at anything else, I can always change. So is there anybody here who grew up in the metric system? So we have 2 people who grew up in the metric system. So do you think in Celsius? Do you think in meters? Okay. Can you convert from meters to feet? So 1 meter is approximately 3 feet. So if you use that as a conversion, it's not perfect, but it's not terrible. But you can essentially rescale by just multiplying anything in meters by 3. Years ago, in one of the most annoying whoopsie moments of science history, there was a probe that was about to land on Mars, and everything was in the metric system except for one quantity, which was in the English system. And so it miscalculated how much thrust was needed for the landing and became a $25 million crater. You have to be very careful what units you are using. Always check what units is this in. But it's often not a big deal to go back and forth between units. And so here, I just want to adjust these so that v and w have length 1, not a big deal. Now, the standard proof and the proof that was given in the notes or the lecture was the law of cosine. And if I have a triangle like this, if this is v, and this is w, and this would be w minus v, and we would calculate the lengths of everything. I think in the notes I did p and q. I don't want to do the algebra proof. And the algebra proof involves the law of cosine. So if this angle here is theta, we love right angles, so I drop a line down like this. If I call this length A, if I call this whole length B, if I call this X, if I call this B minus X, if I call this H, and if I call this C, I have 2 right triangles, and the right triangles both involve an H. So X squared plus H squared is A squared, so H squared is A squared minus X squared. So we would get H squared is A squared minus X squared, and that's also equal to C squared minus B minus X squared. But we know what x is. X is just a cosine theta. So if we just do some algebra, that's going to give us c squared is a squared plus b squared minus 2ab cosine theta. And that's the law of cosine. When you look at this, you should always ask, is there anything I know that looks like this that might be a special case so I can check and see if the law of cosine is reasonable? Any good choices for theta? What might be a good choice for theta? Why 60? So we know what the cosine of 60 is, but now we have to relate the three sides of the triangle A, B, and C. So 60 is not a bad angle, but there's a better angle to choose than 60. It has a really nice cosine.
45?
Even better than 45.
90.
90, right? Why is 90 the best? It's the Pythagorean theorem. If you take theta equals 90, this vanishes, and you get c squared is a squared plus b squared. So you see the Pythagorean theorem is a special case. Yes?
Oh wait, never mind. So I was looking at that triangle and I was thinking if theta is 90, then how would that be a triangle?
Right, but
Yeah.
yeah, the theta is, yeah. And so that would basically be like this. Does this mean we just proved Pythagorean theorem? No. Why not? What did we use to prove the law of cosine? We used the Pythagorean theorem. Right? You can't prove the Pythagorean theorem by using the Pythagorean theorem. But you can at least check and see is your final answer consistent. So this is the standard proof using the law of cosine. I am going to show you a new proof that uses linear algebra. And it's going to allow us to talk about better ways of looking at what's going on and trying to see fundamentally why is something true. A lot of times you can follow the algebra line by line by line and be left with going, how the hell did they think of doing that? Why would they do this? And okay, at the end of the day, everything works out, but I have no idea why that calculation is that way. Later this semester, I will probably talk about a bet I made in graduate school to teach me, took me 50 pages to do the calculation by just doing the algebra. And this was a friend trying to teach me a very valuable lesson. When we're trying to do the proof, we can assume without loss of generality that V and W have length 1. Because if they don't have length 1, we can always just rescale, unless one of them has length 0, but if they have length 0, then we know the dot product is 0, and the angle is going to have a cosine of 0, so everything is fine. So without loss of generality, big log, we can assume the length of V is the length of W is 1. So that means that you have 2 points on the unit circle. And then again, you should assume that what I'm drawing is actually a circle. Where should we have V pointing? Where do you want V to point? There are infinitely many choices. One of them is really good. The x-axis, right? You know, let's assume this is V. So here is V at vector 1, 0. And I'll assume my W is in the upper right quadrant. So here is W. If this is theta, what are the coordinates of W? What's the x-coordinate of W? So this has length 1. This is theta. What's the length down here? Cosine theta. This is our trigonometry. The cosine of theta is adjacent divided by hypotenuse. Since the hypotenuse is 1, this is just going to be cosine of theta. What's the height going to be? Sine of theta. So I'm going to try to write that. So it'll be sine of theta. So the coordinates of W are cosine theta, sine theta. So what is V dot W? It's going to be 1 times cosine theta plus 0 times sine of theta equals cosine of theta. Aha! That's what we're trying to show. Now, the dot product theorem is true in more than just the plane. I am focusing just on the plane. I'm trying to just give you a sense of why it's true. Always look at the simplest case and build intuition from it. We saw in the last class that intuition could be wrong. 16 over 64 is not 1/4 because you cancel the 6s. But try to gather some data. Think of that as experimental. All right, so now what you would want to do is imagine instead, we now have, say, V is over here, and W is over here. What we would like to do is we would like to rotate them back and show that as we rotate, we don't change the dot product. We don't change the value of V dot W as we rotate. Another way of saying this is we want to change our coordinate system and have the coordinate system go through V. Well, the problem is when we write V dot W, we're writing things down in the coordinate system. So whenever I give you a vector, if I write it down, I have to choose my coordinate system. A lot of times the coordinate system is natural and almost forced on you. If you're in Manhattan and you don't measure things north, south, east, west, you gotta have a damn good reason why you're not doing that, because you've got a grid. You can do whatever you want, but there should be a reason. In World War II, in London, they took down street sign names. Why would they take down street sign names? To make it harder for spies. Because that people in London knew how to get around, they didn't need the sign, even somebody who wasn't. So there was a natural reason for doing something like that. If you have a beautiful grid and you, no, come on. So we want to have our coordinate system going through there, or equivalently, we want to rotate our matrices back. And so what I'm going to do now is, I'll imagine that this is an angle of theta. I'm going to talk about a rotation matrix. So our theta is cosine theta minus sine of theta, sine of theta, cosine of theta. And I'm going to see what does this matrix do when it acts on a vector. And it's okay if you're not following everything that I'm doing here right now. The goal is to just give you a little bit of a sense of how things work. So if I take R theta and act on 1, 0, this is cosine theta minus sine theta, cosine theta, acting on 1, 0, I get cosine theta, sine theta. So what that does is R of theta takes the x-axis and rotates it theta degrees up, or theta radians up. If I take R of theta and I act on 0, 1, the y-axis, I would get cosine theta, sine of theta, minus sine of theta, cosine of theta. 0, 1 is minus sine of theta, cosine of theta. It takes the y-axis here and moves that theta radius. So the effect of this on the x-axis and the y-axis is to shift them counterclockwise theta radius. Now what you do is you take an arbitrary vector and you show that it shifts it by theta radians. I'm not going to do that calculation. This is not a linear algebra class. I'm just trying to give you a sense of what's going on. That this matrix rotates you by theta degrees. If I did 2 theta, how much would it rotate you by? So if I replace theta with 2 theta, how much would it rotate you by? 2 theta. What if I replace theta by negative theta? What would it do? Negative theta. So instead of rotating you counterclockwise by theta, if I put in negative theta, it rotates you clockwise by theta. So it's going to be the inverse, it's going to undo things. So this rotates by theta clockwise. Okay. And so now that we have that, we can look at what would happen if we start off and if we rotate our vectors. And again, I only want to do enough of this calculation to show you that it's reasonable. And then what we're getting is we're getting the law that the dot product is equal to the cosine of theta. We see that in a special case without too much trouble, when one of the vectors is aligned with the x-axis. And then the whole point is linear algebra tells us that's the only case that matters. So V dot W is V1 W1 plus V2 W2. And one way to view all this is if I give you V, we write V as a column vector. But we can also look at it as a row vector, and we use the transpose to switch the columns and the rows. I will often be careless in this class, but if we want to look at V transpose W, that's going to be V written as a row vector, and W written as a column vector. So if you think of this as matrix multiplication, this is a 1 by 2 matrix. This is a 2 by 1 matrix. We can have them combined because the last of this is the same as the first of this. And this is going to give us a 1 by 1 matrix, which is a number. V1 W1 plus V2 W2. Okay. So another way of writing the dot product is it's just V transpose times W. If I give you matrix A, B, C, D, the transpose of that is A, B, C, D, because I flip the rows and columns. If you do the calculation, if I have V acted on A and I take the transpose, this is the same as V transpose A transpose. So when you take the transpose, you flip the order and take the transpose of each. These are just calculations you can do. It's okay if you're not following every single step. I just want you to have the broad overview. So if I now have, I rotate V by R, and I rotate W by R theta, so I rotate them both by the same amount, and I want to find the dot product, I would just have this. And now I just expand things. I'll have V transpose, R theta transpose, R theta, W. All right, so now I want to do a little bit of a calculation. So here is R theta. It's cosine theta minus sine of theta, sine of theta, cosine of theta. I'm doing this slightly differently than section 1 because if I did the same calculation twice in a row, I'd go crazy. So I take the transpose of this, and so the first row becomes the first column, cosine theta minus sine of theta, and then this becomes sine of theta, cosine theta. It turns out that this is just R of negative theta. And the reason is cosine is an even function. The cosine of theta and negative theta are the same. Sine is an odd function. The sine of negative theta is negative sine of theta. So if I plug in the negative theta here, I get negative sine of negative theta, sine of theta. Down here I have sine of negative theta, negative. So R theta transpose is really just R of negative theta. And so when I plug that in here, I get V transpose, R r of negative theta, r of theta, w. Ooh, I start with w, I rotate it by theta, I then rotate it back. So if I rotate by theta and I rotate back, what do I get? So I start, I rotate by theta, and then I rotate back by theta. Not zero. I start with w, I rotate it by theta, and I rotate it back by theta. Where do I end? W. And if you go through and if you do the algebra, if you actually do the matrix multiplication, you get the identity matrix. If you can think about it geometrically, I rotate and then I undo. So I just get V transpose W. Ah! What that means is the dot product doesn't change if I rotate both vectors. And this is a higher level of trying to see why it's true. That the reason it's true is because the dot product doesn't change, and I can now just reduce everything to that one special case. Okay, so this is the dot product. Extremely useful point. Any questions about this? Okay. So building on our success with the dot product, what should we study now? The cross product. Right? The lecture almost gives itself. And so the cross product gives us the area. And again, I will focus for the most part on 2 dimensions. We will occasionally use 3 dimensions and higher. If I give you, here's W, V cross W is perpendicular to both of them, and its magnitude is the area of the parallelogram spanned by V and W. What kind of number is area? It's a scale, but what kind of numbers could be areas?
Positive.
Almost.
Or zero.
Positive or zero, so non-negative. So when I take the determinant gives us the signed area. It's very similar to calculus when we do integration. If I integrate from 3 to 5, that's the negative of integrating from 5 to 3. If I go backwards, I switch and I add a negative sign. So for the determinant, V1, V2, W1, W2, this is V1, W2 minus V2, W1. This is the signed area. Okay? So the first thing is this formula reasonable? If I double the length of V, what should happen to the area of the parallelogram? Double. If I triple the length of V, what should happen? It should triple. And if you look at this formula, if I double V, I double V1, I double V2, it doubles. Each term on the right-hand side involves V and W only, has exactly one factor of V in each place. Has exactly one factor of W in each place. This is a good formula. So as long as my vector does not have length 0, I can always adjust to have it have length what? If it has length 0, what's the only vector that has length 0?
Vector 0.
Vector 0. Okay, well then V1 is 0, V2 is 0, the area is 0, not a big deal. So without loss of generality, let's assume the length of V equals the length of W equals 1. And again, I'm trying to build intuition for these formulas in special cases where I can do the calculation without any trouble. And then we say, and thou shalt appeal to linear algebra, and linear algebra tells us that as you rotate, the formulas just rotate and follow nicely. So we now have 2 unit vectors. Where should V1 point? Where should V point? X-axis. So, as always, here is the pointing in the direction of the x-axis. And now we have W over here, and W will be cosine theta, sine of theta. And so if we calculate the area, it's 1, 0, cosine theta, sine of theta. So according to the determinant formula, it's 1 times sine of theta plus 0 times cosine of theta or sine of theta. If, however, I look at the picture, well, if I look at the parallelogram, I just need the height. And the height is just sine of theta. The hypotenuse is of length 1. So the area of the parallelogram is clearly sine of theta. And the determinant formula gives us sine of theta. So claiming that this determinant thing gives us the area is at least reasonable. It works in the special case. So I have limited psychic ability. I can read the minds of students, especially in classes that I have taught longer than you've been alive. So I first started teaching multivariable calculus in the 90s. There is no one here, I believe, who really wants me to go through the algebra of rotations until it all works out. I will take the picture from the mathematics code that I wrote this morning and I'll hold it up over here. I will maybe email it to people later. If you want to, I am happy to meet with you individually or just write this up in greater detail, but you can do the algebra just as we did for the dot product and it will work. But the idea, the goal is to use our time productively and say, look, this is not a class in linear algebra. We've done enough linear algebra to show that this is reasonable, that as you do these rotations, certain quantities are unchanged under rotation. And it turns out that this determinant is also unchanged under rotation. You can do a very similar calculation. We only have to do this one special case. There is one other case that is worth doing directly. Let's imagine W is alpha times V, so it's alpha V1, alpha V2. This means V and W are in the same direction. What should the area be if V and W are in the same direction? It should be 0. And so when we go through, we would have V1, V2, alpha V1, alpha V2, and we would get V1 alpha V2 minus V2 alpha V1, which is 0. Good, our intuition works. We should get 0 for the area when they're aligned, and we do get that. So this is hopefully enough of a proof that the determinant really is giving us the area of the parallelogram. Now, unfortunately, we try to do things in general. Here's V, here's W, here is theta, and this is going to be the length of W times the sine of theta. We don't have anything nice to sine of theta. What trig function of theta do we have something nice for? So what did we do today that has something nice involving a function of theta? The dot product. So what does the dot product do? Is the cosine. So we have something in terms of cosine. Wouldn't it be wonderful if there was a formula relating sine and cosine? And there is, right? What do we have? What's the relationship between sine and cosine?
Sine squared plus cosine.
Sine squared plus cosine squared is 1. So the sine of theta is the square root of 1 minus cosine squared of theta. And so maybe we can use our dot product formula, put it in here, do some algebra, and when the dust settles, we will get our formula for the area. So if I ever get a coat of arms, I will have a hammer on my coat of arms. Does anybody know the law of the hammer or the principle of the hammer? If all you have is a hammer, pretty soon every problem looks like a nail. And there's a lot of ways to interpret this. One way is if you are really good at something, no matter what you are given, you try to find a way to work your skill. If you watch politicians at debates, it doesn't really matter what politician, after about 30 seconds, whatever question they're asked, they migrate to whatever they wanted to talk about. And they find a way to put that in. The better you are, the more smoothly you can make those transitions. The great Richard Feynman, Nobel laureate in physics, undergrad, MIT, grad school, Princeton, had a reputation for being able to do integrals that no one else could do. And when people were stuck, they would come up to him and he would look at it with the figure. And they would be amazed at how quickly he got it. And in one of his books, he talks about how he does this. He says, well, look, I have friends, the people coming up to me in math and physics are smart people. If the standard techniques would have worked, they would have done them, solved it, and not come to me. So I'm not going to bother by spending any time on the standard techniques, because clearly they've already tried that. Most people don't know the technique of differentiating under the integral sign. Let me try that first. And he had a reputation of now being able to do these problems very quickly. Work with what you know. We know things about cosine. Can we somehow convert sine to cosine and work that in? So much of math is finding a way to do the algebra and to extract something you know. The other lesson, if you have a hammer, is go to the land of the screwdriver. There are smart people there too. If they could have solved the problem using screwdrivers, they would have. And so you have the opportunity to collaborate with people who have different skill sets. And so I've written papers in marketing, sabermetrics, statistics, geoscience, physics, computer science, so many different fields, because I can transfer what I've done and I have a different perspective. And that's extremely valuable. So if any of you are interested in trying to handle some research on a variety of problems, send me an email. I have a bunch of things at different levels, a lot of people who are looking for things, and you already have enough skills to be useful. So the whole point here is to justify the algebra proof in the book. We know something for cosine. So the game has to be take the sine, somehow write it as cosine, and then somehow work in the coordinates of v and w, because that's what we're given. So again, the goal is so that when you're reading these books, you have at least some idea of how they're coming up with their proofs and their approaches. Okay. Any other questions on the area here before we move on to the cross product? And you might notice that this is almost like a special case of the cross product. Okay, so what we have done so far is, highlight looking at special cases, building intuition there, and then seeing how that special case can be propagated to the general. Now it is time for the cross product, and probably one of the greatest abuses of notation in So we start off with a 3x3 matrix, and in the first row, we put I hat, J hat, K hat. What kind of quantities are I hat, J hat, and K hat? They're unit vectors. And in the next two rows of the matrix are numbers. So we look at I hat, J hat, K hat, V1, V2, V3, W1, W2, W3. And we take the determinant. Yeah. This is highly illegal, but we're just using this as a mnemonic to get to the formula. And the way it works, and it only works in 3 dimensions, is we take the first two columns and copy them down. So V1, W1, V2, W2. And then we go diagonally like this, and those products all come in with a plus sign. And then we go diagonally above, and those all come in with a minus. And so now let's just expand. So the first one is going to be I hat V2, W3 plus J hat V3, W1 plus K hat V1, W2. Now, for the next one, we have negative K hat V2, W1. Where should I write that under? Should I write it under the I hat term? Where should I write the K hat V2, W1 term? Under the K hat. So we'll write a minus K hat. So I'm always going to write V first, V2, W1. The next one will be minus I hat V3, W2. I'll write it over here. Minus I hat V3, W2. And the last will be minus J hat V1, W3. So if I collect, the first coordinate is V2, W3 minus V3, W2. The second component is V3 W1 minus V1 W3, and the last one is V1 W2 minus V2 W1. Anybody notice anything about the components? What patterns do you see? What do you notice about the first component? 2, 3, 3, 2. What's missing? The first component doesn't have any ones. What about the second component? Doesn't have any twos, and in a shocking move, the third component has no threes. Each component has a sum and a difference. I'm always writing the V's first, goes V2, W3, W3. Okay, so they just alternate. And here, the first component, I start with a 2, the next number. The second component, I start with a 3, the next number. And the third component, what comes after 3 if you wrap around in a circle? 1. And so this is a way to remember the formula. And so we define this as the cross product. And it turns out, if this is V and this is W, the magnitude of this is the area of the parallelogram, and its direction is perpendicular to both V and W. When you look at this, does it look like this is perpendicular to V and W? I don't see it. Here is V cross W. Here is V. V1, V2, V3. While I have spent a lot of today talking about, trying to prove things from a deep fundamental understanding, it's also not bad sometimes to just roll up your sleeves and do algebra. If we take the dot product of this with V, what happens? Well, we'll have V1, V2, W3, and over here we'll have a negative V1, V2, W3. Those cancel. And so if you do all of the algebra, you can show that V cross W dotted with V is 0. Is it 0 the number or 0 the vector? The number, because we have a dot product. So this proves that the dot product is actually perpendicular to V. A similar calculation shows it's perpendicular to W. If you think about it, if I have a vector, what is the dimension of the space perpendicular to that vector? If I have a vector in free space, what's the dimension of the space perpendicular to it? Well, it's going to be perpendicular, so I have to be spinning around like this. Just like this over here. What's the dimension of the space? I had 3 directions initially. I have to be perpendicular to this. How many dimensions are left? 2. Basically, what's perpendicular to this would be a plane. So if you look at what's perpendicular to a vector V, that's a plane. If you look at what's perpendicular to W, that's a plane. So if I have 2 planes, this is why I have 2 pages of notes today, what's going to be the intersection of 2 planes? A line. And that line is where V cross W lives. V cross W lives on the line that intersects those 2 planes. The question is it pointing out or is it coming in? And this is what we have the right hand screw. If I take my right hand, if I do V cross W, I come from V towards W, and my thumb points in the direction of V cross W. This is just a mnemonic to remember which way things go. If I do W cross V, I have to turn my hand like this at first, but you guys are with it, and I go like this, and now I'm pointing into the board. And if you think about what goes on, if I flip the rules of V and W, I'm going to flip all of these by -1. And so when you do the algebra, W cross V is negative V cross W. If you think about what's going on in a more fundamental level, the dot product, can I switch the order of the vectors without the dot product changing? So is V dot W is W dot V?
Yes.
Yes. And what's really going on is the dot product involves cosine of theta. If I look at the cross product, that's negative W cross V. And the reason is the cross product involves the sine of theta. And if you switch theta to negative theta, sine changes, but cosine doesn't. That's why the cross product is going to be different. Okay? So we have a formula for the cross product. We proved that it was giving us the area of the parallelogram in the special case where we were in the plane and we were doing determinants. You could do all of this linear algebra again with rotation matrices. Now you have the joy of rotation matrices in three-dimensional space. If you had to, where would you choose your first vector to be in three-dimensional space? So you've got a whole sphere of choices. Where should your first vector point? The x-axis. So your first vector points on the x-axis. Now you have a second vector. If the second vector is in the same direction as your first one, you're done. It's going to have the area 0. If not, where can you assume your second vector lives? How should I rotate? Where do I want to put my second vector? Make it live in the... Well, I can only make it live in the y-axis if it's perpendicular. So it's a good start. So make it a little bit weaker than the y-axis. Where should it live? So now I don't necessarily want to make it in the first quadrant, but I could make it in the xy plane. I can always rotate things so that it's in the xy plane. And so I can, and then, if I'm looking at something like this. And so really, it is enough to just do that special case where we said our first vector was 1, 0, and the second vector was cosine theta, sine theta, and that gave us the area. The cross product will give us the area in general. It's just higher level algebra to do this. So you have possibly seen something like this before. How many of you have ever watched the TV show Friends? A little bit more than the first half. So I did not start watching it until late in the series. Chandler and Monica were going through their dating and getting married, like when my wife and I were doing similar stuff. And it was fun watching the documentaries. Every episode of Friends but 2 has a title that begins the same way. What is the title of every episode but 2 of Friends begin with? The one with. And so when I teach the proof of the fundamental theorem of calculus, it is the lecture that I title the one with the mean value theorem. The mean value theorem is one of my favorite theorems in math. It is essentially a no-shit theorem. I forgive the language. Imagine your average speed is 50 miles per hour. Is it possible that you're always traveling below 50 miles per hour? No. Is it possible you're always traveling above 50 miles per hour? No. So this is why I call it the notion, because at some point you must be traveling the average speed, unless it's a Star Trek and you have a transporter and your speed can instantaneously change. So as long as we assume things are continuous, and now this is the intermediate value theorem, which you mentioned earlier. The intermediate value theorem implies the mean value theorem. So f is continuous and differentiable on AB, exists AC and AB, such that the instantaneous speed at C is f of B minus f of A over B minus A. Here A is B. Here is my average speed, and there has to be at least one point, here there's actually 2, where your instantaneous speed is the same as your average speed. And the intermediate value theorem says if you start off at 20 miles per hour and you end at 80 miles per hour, you have to hit all the intermediate speeds. Does anybody know a simpler case of the mean value theorem that has its own meaning? It's a special case where you assume something about f of A and f of B. If we assume f of A equals f of B equals 0, this is Rolle's theorem. And in this case, here's A, here's B. It just tells you that there's some point where your first derivative is 0. If you look at the mean value theorem, I've been screaming bloody murder for about a week now about choosing the right coordinate system. Rather than having the origin here, where should I move the origin? Wouldn't this be a nice place to put the origin? Where should I orient the x-axis? The x-axis should point in what direction? Yeah, this line. So here, choose these as your axes. And now the mean value theorem just becomes Rolle's theorem. So you can just do some kind of conversion, and this is very similar to the conversion from Celsius to Fahrenheit. You do some kind of conversion like that, you can reduce the mean value theorem to Rolle's theorem. How many of you have seen Rolle's theorem? Okay. How many of you have seen the mean value theorem? How many of you have seen the mean value theorem but not seen Rolle's theorem? Okay. So the mean value theorem is a consequence of Rolle's theorem. So rather than proving it in general, you can actually prove the special case and then get everything from that special case. And this is one of the big themes of this class, is rather than doing painful calculations in general, let's look at the simplest, nicest case I can think of, show that everything works out in that case, and then say, and then we appeal to some results from linear algebra or other subjects that say, as we transform, the result holds. All right, so this is a good place to stop. This should hopefully give you a better sense of how the semester is going to work. If I did not cover things that you wanted, please send me an email, and I'm happy to work them into either the next lecture. I have deliberately not given you homework due today to push us a little bit further in lectures from where homework is assigned, so that you have a little bit of a cushion. This way we're not learning something on Wednesday and then you have to hand in the homework immediately on Friday.